Chapter 8, Probability and Statistics. Estimating with confidence. What we're going to do in this chapter is talk about confidence intervals. In section 8.2, we'll do confidence intervals for proportions. And in section 8.3, we'll do confidence intervals for means. But in this one, we'll sort of introduce the idea of confidence intervals. So, after this section, you'll be able to determine the point estimate and margin of error from a confidence interval, interpret a confidence interval in context, interpret a confidence level in context, describe how the sample size and confidence level affect the length of a confidence interval, explain how practical issues like non-response undercoverage, response bias, can affect the interpretation of a confidence interval. So this is an activity. So suppose I, your teacher, pick a mystery mean, a value that I've calculated with my calculator. Let's say that we used this statement, mean rand norm M 2016. So what does that mean? We've taken a randomized set of data, but it's using the normal distribution to do that. So M is this mystery mean that you don't know, it's a secret, and 20 is the standard deviation, and 16 is the number of values. And the mean all the way to the left of that means I've taken the average of these 16 values. So I've picked this mystery mean, whatever it is, and using that as my guide with 20 for standard deviation, I can find, I guess, another mean. And when you do that, let's say you get 240.79. So what was my mean, my mystery M? Well, it could have been, I guess, 240.79, but it didn't have to be that. In fact, if you did it a bunch of times, mean, rand, norm, with the, I guess you'd have to choose something. M doesn't necessarily have anything in it right now in your calculator. But if you choose something like 240, it'll give you some values like this. So for you to figure out exactly what my mystery mean is would be very hard. But you could give me an interval of reasonable values for that population mean. So, if you do this several times, rand norm, and there's one that you got, that list, and then you take the mean of that, you might get, 242.147. Or do it several times, you might get these different numbers. Notice none of these are 240.79, which was what we got the first time on the previous slide. So just whatever we picked for M, to find that exactly, pretty impossible. So what you're looking for is not a point estimate like M would be. This 240.79 is a point estimate. All the numbers in that box above, the 242, the 236, the 243, all these are point estimates. They're a guess at what that mystery mean might have been. A point estimate is pretty hard to find, or the point estimate isn't hard to find, but the actual value is hard to find. So what we're going to do is give an interval. Make sure you understand, though, if you wanted to give one number to estimate an unknown population parameter, what would that be? Well, it would be the sample parameter. For the population mean, you would use the sample mean. For the population proportion, you would use the sample proportion. That's your best single value estimate, a point estimate. So a point estimator is a statistic that's from a sample, that provides an estimate of a population parameter. The value of that statistics from a population sample, rather not a population, from a sample is called that point estimate. An ideal point estimator would have no bias and low variability. But variability is always present. You saw that when we did that box of that mean rand norm stuff. There's always going to be something different. It gives us a different answer. So acknowledge this repeating could give several different answers. Remember, is the value of the population mean exactly 240.79? Probably not. But it's somewhere around that. So how do we sort of give an interval that may give us this? How would the sample mean vary if we took many of these? Well, go back to our bell-shaped curve. If the standard deviation is 20, we could take a bunch of these samples, size 16, and we could find mu, the unknown. If we took all that sampling distribution of sample means, we could find it exactly, but we don't do that. We just take one sample and try to do it. But we should be within, depending upon how far to the left and right we go. Now remember, when we use the population mean, and standard deviation is 20, when we do this, this is the samples, when we do the sampling distribution of the sample means, we have to divide by that square root of n because this gets skinnier. So, don't expect to find it exactly. How accurate do you want to be? Remember that 68, 95, 99.7 rule? The 95 means that 95% of all samples, size 16, will be within 10 standard deviations of the mean. So, 240.79 plus 10, 240.79 minus 10 will give us an interval that we can say we're 95% confidence will have the true population mean mu. The mu plus 10, the mu is minus 10. Now this will probably have our sampling distribution x bar. Therefore, if we add and subtract to x bar, we should contain this mu, if that makes sense. If mu plus or minus 10 gets 95% of the time this x bar, then the x bar plus or minus 10 will about 95% of the time get mu. So we're going to use that with the x bar instead of the mu to say that's a good interval. So if we estimate mu lies somewhere between the interval of 230.79 to 50.79, we'd be using an interval, a method that captures this true mean for the population in about 95% of all possible samples of this size. So this is the big idea. The sampling distribution of x bar tells us how close to mu the sample mean x bar is likely to be. All confidence intervals we construct will have this similar form. It'll be estimate, that's the x bar, plus or minus a margin of error. You might have heard this on TV. Finding a C%, that's the confidence interval percent, like 95%, 90%, 99%, gives an interval of plausible values for the parameter mu. The interval is calculated by using the point estimate, that's the x bar, or perhaps the p-cap for a proportion, plus or minus a margin of error. The difference between a point estimate and the true parameter value will be less than that margin of error in about C% of the samples. At confidence level C gives us overall success rate using this method. And C% of all possible values. The method would yield an interval that captures that. So, the confidence level is the overall capture rate if the method we talked about is used many times. The sample mean will vary from the sample to sample to sample to sample, but in about 95%, if we use 95 here for C%, that will capture it. Let's look at this again. Remember, this is the population. That's the actual mean, the standard deviation. We take a bunch of simple random samples, and about 95% of these intervals will capture. And this is a nice picture. I think this helps an awful lot. Here's the actual mean mu. And if we look at these intervals, this is the x bar where the dots are, and right and left with the error. And you notice a few times, like this one, that interval did not contain mu. But almost all the others, in fact all the others listed here, did. And that's where they get this idea of 95% will contain the parameter. So how do you interpret these confidence intervals and confidence levels? It's the same all the time. You say the same thing. We are C%, like 95% confident that the interval from, and we did this before, 230.79 to 250.79 captures the actual value of the population mean. The confidence level, almost the same thing. 95% confident. So this is where the quotes start. If we take many samples, and that's important, of the same size from this population, about 95% of them will result in an interval that captures the actual parameter value. Confidence level tells us how likely that this method we are using will produce an interval that captures the population parameter if we use it many times. In other words, we've got these numbers. Gives correct results 95% of the time. The level does not tell us the chance. It's not a probability. It's different if we do this many times, about 95% of the time, but it's not really a probability that it'll capture it. Although I think you can sort of think it that way. The confidence interval gives a set of plausible values. And the confidence level is estimating population mean. We can use this with the mean or proportion or standard deviation, although we do just mean and proportion. So, let's do one. First of all, why settle for 95%? Why not do 99%? Why not 100%? Well, to get 100%, remember that our bell-shaped curve goes on to infinity right and left. So getting 100% maybe not a good idea. That's a pretty wide interval. Even 99% is a wide interval. Just think of all the difference. The 68%, 95%, 99% was the 1, 2, and 3 standard deviations from the mean. The bigger the number for the percentage, the wider that interval has to be. So this margin of error really is how many standard deviations you're going to go. So if we look down here, this 240.79 plus or minus that 2 times 5. This is the number of standard deviations, and 5 was the standard deviation. So this is really x bar plus or minus 2 sigma sub x's. And so in general, the statistic plus or minus critical value. The critical value is that 2, the number of standard deviations. And then the standard deviation of the statistic was the 5. Now,